Okay, so as a particle orbits in a central force, it feels an effective repulsion, let's say, um, which an effective outward force, which is due to its again a sort of centrifugal effect, and so when we write the when we make the substitution here, mu is equal to r times r, then we see that term just pops right out. Okay, so we can, in principle, we could proceed then to rigorously solve this differential equation for mu, and then we could, once we know mu, then by dividing mu by r, we get the radial functions r, big R. But this is a long and drawn out sort of procedure, okay? And so we're not going to show the details. We're just going to talk about the results, okay? So for the hydrogen atom, so first of all, up till now, we have not assumed any particular form for U of R other than to say that the potential energy of the particle is just a function of the distance of that particle from some fixed central point, some central origin. Okay, that's all that we've assumed. We haven't assumed a particular form, but for the hydrogen atom, then we have a Coulomb potential. Okay, the negatively charged electron is attracted to the positively charged nucleus, and the potential energy is given by Coulomb's law, minus e squared over 4 pi epsilon naught r. Epsilon naught, again, is the permittivity of free space, and r is the distance between the electron and the proton. Okay, so substituting in that potential into the previous equation, okay, then if we express, and by basically going through again a rigorous derivation or rigorous solution where we express the solutions as a power series, and we require the solutions basically to be normalizable, that is square integrable, then we can eventually arrive at the energy eigenvalues. Okay, so the energy eigenvalues are negative minus the mass m times e squared, again the charge, the elementary charge squared, excuse me, divided by 2 h bar squared by 4 pi epsilon naught squared, and times 1 over n squared. Okay, I paused there for a second because I realized that I had originally wrote down e squared, that is the elementary charge squared, but it's actually e to the fourth. Okay, so I've made that change. Okay, and so these are the energy eigenvalues, and it turns out that this is exactly equivalent to what Bohr found. Okay, in his model, he did not give a quantum mechanical justification for it, but it nevertheless turned out to be the same. It turns out to be the same constant. Okay, and so we see that the energy eigenvalues are proportional to 1 over the principal quantum number squared. So n is now a principal quantum number, and it's an integer that runs from 1 to infinity. Okay, we see that the energies are negative, meaning that these are the bound states. Okay, so these are the these are the bound states, and they're essentially an infinite number of bound states, because the potential energy is only 0 at infinity. Okay, and so there are essentially an infinite number of bound states, and you have this constant here is just we'll call that E1. That's the ground state energy.